Okay, in this video, we're going to look at the effect that the changing parameters a, h, and k have on the function f of x equals x squared. The ideas here, though, can be really worked for any function. So first, we'll just look at the effect that the function has on the parameter, or on the, I'm sorry, that the parameter has on the function. So you'll recall that when you multiply by a coefficient, it causes the function to stretch vertically. I want you to think about that as moving up, not moving to the side. So this point becomes this point up here. So the whole function got stretched in a vertical way because things were multiplied. So 0 stays the same. So you'll notice the distances between these are not the same at every point because it was what it multiplied by, not what it added. The next parameter is h. Let's set a back so we can study h on its own. H causes a graph to shift left or right. Oh my God. So when you slide h, you're just causing the graph to shift over. In this case, the points all move exactly the same amount. So this case, if you were to draw a line between the point and where it goes, every line that's drawn would be exactly the same distance because it's moving exactly over. It's what we call a rigid transformation. Finally, the last parameter would be the k parameter. So we set h back to 0. If you have a k, you slide up and down. Notice this is not the same as when we used a and we multiplied. Even though it might not look it, these still are all exactly the same distance apart because this went exactly 10 units up. So every green to blue is always 10 units apart when you slide something up and down. So now we'll look at the effect that those parameters have on the derivative. When we do that, we're going to actually draw ourselves a tangent line, and then we can use that tangent line and see how the slope of that tangent line changes when we change each parameter. I'm going to work backwards here. So I'm going to say what happens when I add a k. So when I shift the function up. So the derivative of f of x equals x squared is 2x. So what happens when I have, say, g of x, which is equal to x squared plus k? And you can see that the derivative here is exactly the same as if I didn't have the k. And that's because these two functions are parallel, these two tangent lines. They have the same slope at the same point. So at 4, both of these functions have exactly the same slope. So that would happen no matter what k was, no matter where k is at each specific point, the two functions have exactly the same slope. So k has no effect on the graph. All right, let's consider the effect that h would have on the graph. So say I slide h over, let's make it 6. Okay, so if you had h of x, which would be x minus h squared. Now, you could multiply this out and put it in standard form and consider taking the derivative that way. Or you could say to yourself, this has the same slope, it's just not in the same place. So these two have the same slope. However, this green function, this x minus h plus k, this shifted function, has that slope when it's 6 units to the right. So this blue function has the slope at 4. This green function has that same slope at 10. So all of the slopes got shifted 6 units to the right. So we can just shift the tangent function or the derivative for the slope exactly the same way. So however you shifted the original function is the same way you can shift the derivative. Another way you can think about this is you can say to yourself, before I go to take the derivative, so before I plug into the function, I'm just going to subtract 6. Now, once I subtract 6, I've taken this green function, I've moved it back over to the blue function, and then I take the derivative. And since the derivatives are the same, as long as I subtract 6, I've gotten back to the exact same function as the others. So you can't ignore the h, but however the h is acting in the original function is exactly the same way that it's going to act in the derivative. Finally, we'll consider a. So if you have a function where you are multiplying by a coefficient, in front of the function, you'll recall that that causes all of the points to be multiplied, all the outputs of the function to be multiplied by that number, it actually affects the tangent in exactly the same way. So as you can see here, this function, this green tangent line, got much steeper than this blue tangent line. Since I multiplied all of my outputs by 2, since I stretched it by a factor of 2, I've also stretched the tangent line by a factor of 2. They work in exactly the same way. So when you take the derivative, you can just multiply the coefficient by the derivative of the original parent function.